So they're also useful properties of the transfer functions. And they're also not terribly complicated, but incredibly powerful. And this is why we like to use transfer functions. And that is if we're having two systems in a row. So I have a system, and then it's followed by another system. And we have an input u and an output y. We can see that the overall transfer function y over u equals to g1 times g2. And we can simply figure this out by calling an intermediate variable in here, which is y1. So y1 equals to g1 times u, and y is equals to g2 times y1. And if we stick the y1 into this equation here, we get y equals to g2 times g1 times u. So you can see that the two systems in series become the transfer function is the multiple of the two individual transfer functions. And we can see this with an example. And so if you have a tank that is drained over a valve, that means that if we have volume V1 in here and we have a height H1, we can describe it with the following equation, and that is the surface area, so the area of the tank, times the height, differential of the height, so how the volume changes is how the height changes, and that is Q in, so here's our Q in, minus Q1. This is our outflow, Q1. And now if this drains like this, it drains through gravity. And then there's another equation that relates the outflow to the height, because I get a higher flow rate, the higher the level is. So we call this the outflow factor, R1 times H1. So this means that the outflow is a function of the level. So the lower the level is, the slower it's going to flow out. And if I stick this in here, this particular relationship, I end up with Qi minus 1 over R1 times H1. So this is also H1. And now I can bring this H1 to the other side, and I get, from this equation, I get A1 dH1 divided by dt plus 1 over R1 times H1 equals to Qi. So in the Laplace domain, I would do a Laplace transfer function. I get A times S times H1 plus 1 over R1, H1 equals to Qi. So I get a transfer function that relates H1 to Qi. So it's H1 over Qi, and we call this G1, and that is 1 divided by AS plus 1 over R1. Okay, so it's a first order process that we describe here. And now imagine, I didn't draw this very well, but imagine you have a second tank. Need this long line that flows into here. So I've got a second tank with a similar outflow valve that makes sure that you are related to the height. So I have a second height, H2. I have a volume 2. I have an area, A2. and I have an outflow Q2. So now I can describe exactly the same system, but instead of H1, I have H2. So I have H2 over the inflow, sorry, H1 over the inflow Q1. And this is now the transfer function of this is 1 over, here should have added A1, A2 times S plus 1 over R2. So if I wanted to put these two things in series, I can simply multiply the dynamics, and I get the relationship between the two systems based on this input function. So this is how this can be useful. And another instance or another property of the transfer function is that you have two systems that we had. This is sort of the property we had before. You've got two systems, and you add them up. And you have an output y. So this is U1 and U2. So you have two inputs. And this is very similar to what we had when we had the input conditions T I of the inflow and the flow rate Q. So the output here was our temperature, that was Y, and this was U1 and this was U2. And we can get a transfer function of the overall model by adding those two transfer functions. So we get Y equals to G1 times U1 plus G2 times U2. And now if you have one input signal, think of a different scenario where you would have a common inflow, a common input signal. G1, G2. And one outflow, we can take the same equation, but we're getting Y is equals to G1 plus G2 times U. So this is called the parallel form. And this one here is the relationship between two transfer functions when they are in series.